On April 10, 2026, the world held its breath as 4 pioneers returned from the deep silence of the moon. Artemis II is more than a technical success. It is a testament to human resilience. But to truly understand it, we have to look beyond the surface of flawless execution. This mission was not simply built on ambition. It was forged through decades of sacrifice, carried by the courage of those who stepped into the unknown and never returned. It was shaped by failure, by loss, and by the heroes who pushed past the limits of what humans can survive, so that others could make it back. It began in January 1967, not in flight, but on the ground, during a routine plug-out test that was never meant to be dangerous. Inside the Apollo 1 capsule, Gus Grissom, Ed White, and Roger Chaffee sat sealed in a pressurized, pure oxygen environment. A single electrical fault was enough. A frayed wire sparked, and within seconds, the cabin turned into an uncontrollable firestorm. Temperatures rose so fast that survival was measured in moments, not minutes. The tragedy revealed something fundamental. The spacecraft itself had become part of the danger. The inward opening hatch, designed for structural integrity, became a fatal barrier under internal pressure. The crew tried to escape, but physics had already closed the door on them. From this moment, NASA understood what had been overlooked. Pure oxygen at high pressure on the ground was too volatile. Flammable materials inside the capsule had to be eliminated. Every fire-sensitive component, wiring insulation, Velcro, foam, cabin materials, was re-evaluated, tested, and in many cases, removed or replaced entirely. Most importantly, the concept of escape was redefined. The hatch could no longer be a sealed structural element. It had to become a rapid release system, something that could open in seconds, not minutes, even under extreme pressure. That design principle still exists today. The Orion spacecraft uses a quick-release hatch system capable of opening in milliseconds under emergency conditions. What seems like a simple engineering feature is, in reality, a direct consequence of Apollo 1. Their loss reshaped the very definition of safety in human spaceflight. Every fire-resistant material, every removed ignition source, every redesigned escape mechanism traces back to that single moment on the launchpad in 1967. Only months later, the Soviet Union ignored 200 known technical flaws to launch Vladimir Komarov in Soyuz 1. It was a mission forced by political deadlines. The spacecraft tumbled in orbit, but Komarov managed to bring it back into the atmosphere through sheer skill. Then the parachutes failed. The main chute snagged, the backup tangled. Komarov hit the Earth at terminal velocity. This wasn't just a mechanical failure, it was a failure of integrity. We learned that even full technical awareness is useless if safety discipline is not enforced. Soyuz 1 showed that known flaws, ignored under political pressure, can become fatal in space. Komarov's fate proved that no deadline justifies an unsafe spacecraft, and that physics never negotiates with ambition. Redundancy must be real, not assumed, and every critical system must function independently under failure conditions. Most importantly, it established a rule still used today. A mission only flies when every known risk is resolved, not tolerated. In 1971, 3 Soviet cosmonauts, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, spent 22 days in space. Their return appeared perfect, until the hatch was opened. The recovery team found them still in their seats, as if asleep, their faces darkened by the effects of vacuum exposure. A small ventilation valve had opened during separation, 168 kilometers above Earth. In less than a minute, the cabin lost all pressure. There was no time to react. They weren't wearing pressure suits. The capsule simply could not fit 3 suited men. From that moment, the rule became absolute. No crew flies without protection against vacuum. Every astronaut on Artemis II wears a pressurized suit during launch and re-entry. No exceptions. Those suits are heavy and restrictive, but they exist because 3 men once had none. January 28, 1986, 73 seconds after liftoff, Challenger was gone, disappearing in an instant, leaving behind a silence that would redefine how humanity approaches the risk of space. 7 astronauts were on board: Scobie, Smith, Resnick, Onizuka, McNair, Jarvis, and Krista McAuliffe, a schoolteacher selected to bring spaceflight into classrooms across America, whose mission was meant to inspire millions of students watching live. What was supposed to feel routine instead unfolded in front of millions of schoolchildren witnessing, in real time, one of the most defining tragedies in spaceflight history. The cause was small, an O-ring seal that failed in the cold. Hot gases escaped, the structure gave way, and the shuttle disintegrated. But the real failure wasn't the hardware. Engineers had warned about this exact risk. They recommended delay. They were ignored. Challenger revealed something far more dangerous than a broken component, a system where known risks were accepted because they hadn't failed yet. That changed everything. After Challenger, NASA redesigned critical systems, restructured safety oversight, and introduced one of the most important features in modern spaceflight: the launch abort system, a tower capable of pulling a crew away from a failing rocket in seconds, because Challenger gave them no way out. 17 years later, the pattern returned. February 1st, 2003, Columbia was coming home after a successful mission. Everything appeared normal until re-entry. The failure had already happened at launch. A piece of foam struck the wing. It wasn't unusual. It had happened before, and that was the problem. The risk had been normalized. During re-entry, superheated plasma entered through the damaged area. Sensors showed small anomalies, then failed. Minutes later, the shuttle broke apart. 7 more lives lost. Columbia proved a brutal truth. A mission is not safe just because it works. Hidden damage is not success, it's delayed failure. This is why Artemis II matters. When NASA delayed the mission, when engineers stopped, tested, and adjusted instead of rushing forward, that wasn't hesitation. It was memory. Challenger, Columbia, a refusal to repeat the same mistake. Because every system on Orion, every layer of protection, every conservative decision exists for one reason: so that this time they come home. The Orion heat shield is not a fragile system of tiles. It is a solid ablative structure, built thick and redundant to survive the extreme heat of lunar return, because we've seen what a single breach can do. Every component on this spacecraft carries a history of failure. But the most important system isn't hardware. Where the 1960s pushed forward at any cost, today every anomaly is questioned. Any concern can stop a launch. Delays are no longer weakness. They are proof that lessons are being applied, that human life is finally valued above schedule. And the cost of those lessons reaches far beyond the astronauts. It includes test pilots who never returned, engineers lost in explosions, and ground crews exposed to invisible dangers. Spaceflight is a pyramid, the astronauts at the top, supported by countless lives beneath, many never remembered. As the Artemis II crew travels through deep space, they are surrounded by the best we know how to build. But uncertainty never disappears. We have learned from fire, vacuum, and structural failure, but space still holds unknown risks. Artemis II exists because others did not survive. It flies on decades of scar tissue. We measure spaceflight in money, but the real cost is human, measured in loss and in the decision to continue with greater care and discipline. Artemis II is not a victory over nature. It is a recognition of our limits and a commitment to push them without forgetting the price. Progress is not a straight line. And today, 4 people come home because we finally learned how to listen.